Hi and welcome back. Today we'll keep talking about skeletal muscle mechanics and force-velocity relationship in particular. I'll first describe you why this relationship exists. We'll talk about this relationship in terms of sarcomeres, myofibrils, and our muscle physiology. And then I'll give you formulas describing this relationship for different use case scenarios. So say running versus walking, which is very useful in clinical and research applications. Let's get started. So first and foremost, we, as per usual, start from the plot. We see that the vertical axis are again muscle forces and the horizontal axis are velocities. One thing you might have already noticed that there are negative velocities and positive velocities. So why is that, you may ask? So negative velocities will be denoting muscle shortening, or what's called in literature concentric muscle contraction. And the positive velocities will be denoting muscle stretch, or what is called eccentric contraction in the literature. So now let's briefly look at this plot before starting to talk about physiology. You see that the force that your muscle can produce is decreasing with the velocity of its contraction. And here we're talking about muscle shortening. So you might have already intuitively knew this when in the gym, for example. Someone gives you a heavy barbell, you start lifting it, but the only velocity you can do that with is very slow velocity. You can't quite just lift it very fast. So that is because of this relationship. Now let's talk about why that's happening. As you remember, muscle is comprised of muscle fascicles. Those contain muscle fibers or muscle cells with a bunch of nuclei, and those contain this myofibrils, but myofibrils are not the smallest one. Myofibrils contain sarcomeres, and sarcomeres are the thingies that contract, right? So why do they contract? They contract because their elements interact between each other. And what are these elements? The elements are thin and thick filaments, which I'm showing here in green and red respectively. So you remember that thick filament has myosin in it, and myosin molecule has this golf club looking like head that interacts and binds to the thin filaments and starts pulling onto it, right? So that's how you generate the force. Now that we discussed in previous lectures. What I didn't tell you is that there is a maximum rate to this interaction. If you try to surpass that rate, none of myosin heads will attach to thin filament. They won't just be on time to do that. So now, that's exactly what you see on this plot right here. If you're trying to increase the velocity of contraction, you're asking your body to increase the interaction between the thick and thin filament, the rate of that interaction. So what you will see happening is with the increase of velocity, not enough cross bridges will form. So you won't be able to produce your optimal force. Once again, if you're trying to increase the velocity of contraction, and that velocity starts approaching the velocity or the rate of cross-bridge formation, the cross-bridges won't be on time to form. That's why you won't be able to generate any force. That's why we don't see force being generated here. It's just zero. So now that you now know about shortening of the muscle and this force-velocity relationship for shortening, let's talk about stretch of the muscle. Counterintuitively enough, you see that the force generated during muscle lengthening is greater than any of the forces generated during muscle contraction. You know, when you think when you're lifting a barbell, you think you're so strong. Not really. You're stronger than when you're elongating your muscle. So now let's talk about why is that. First of all, I need to tell you what this F naught is. And the F naught, see how it corresponds to the velocity of zero. F naught is the isometric force, maximal isometric force, so the force that your muscle can generate when you're not moving. It's the maximal isometric force that your muscle can generate. Now, this maximal force, the F max of this force-length relationship, for lengthening is equal to about 1.8, 1.6 of the isometric force of the isometric contraction. So now you may ask, why is that? What is happening? Now let me remind you, in sarcomere, there is another protein called titin. And you remember the role of titin is kind of pulling onto the thick filament. And titin itself acts kind of like a spring. That's why I drew it curvy here. So now, what is happening? And this is one of the theories. People are investigating this topic these days. But one of the theories is that during muscle shortening, titin, when it recoils, starts storing the energy, kind of like a spring, the energy of the shortening, and then when you start lengthening your muscle, it releases that stored energy that leads to increased forces during muscle lengthening. So hopefully that is understandable. And now let's move to the formulas, the most exciting part, describing all the physiology behind this force velocity and used in various experiments and research settings. The first one to describe force-length relationship was Hill, and he did it in 1938, about 100 years ago. So what he did is he measured the experimental data and then described it with this rectangular hyperbola. So now you see there are a bunch of constants in there. So if you use these equations for research purposes, what I advise to do is to search constants that are specific for the species you're analyzing, so say mice, cats, or humans, and then for muscles you're analyzing. There are a lot in the literature. The ones I chose here are specific for cat. So now let's talk about problems with this equation. So I drew it here, I drew the curve here that this equation describes. So you see how this curve at high velocities of concentric contraction starts crossing the velocity axis and going down, generating negative forces. What is the problem with that? If you start modeling, say, running, unexpectedly, you will be generating negative forces during running in the same muscle that just generated positive forces, just an iteration of the velocity ago. So that may lead to destabilization of your simulation or whatever you're researching with those equations, and may lead to some confusion in your results. Now, how to overcome that? So in 2004, Yakovenko and his colleagues published a paper with a different equation, modeling the same relationship here. The difference is this equation, or this curve, I should say, is not crossing the v-axis even at the maximal velocities. And how does it look? It's just two exponents right here and other coefficients. Again, this one describes a relationship for cats. Now, if you want to use it for humans or for mice, you will need to probably refine some of these coefficients. Now, other group of people also decided to overcome this issue because it's kind of apparent. And this Eggenberg and Pearson published another paper in 2005 where they described curves that kind of look like this. What's the problem with this curve? So you see how at the maximal velocity, the force that is generated is about 0.3 from the isometric force value, so this F naught we discussed on this axis here. So that is also not something that's happening physiologically. So you have two extremes and you need to be somewhere here with your equations. Now, these equations, I should say, only describe the concentric part of the muscle shortening, or the muscle contraction, sorry. So now let's talk about equations that describe the full force-velocity relationship if, for some reasons, you need to model that. The two papers that describe force-velocity relationship for both concentric and eccentric contraction were published by Felon and Silva in 2003. You're already familiar with these papers from our previous lecture. So now let's talk about what each one of them proposed. So Felon proposed that the force will be 0 for the velocities smaller, and we're saying smaller because the velocity of the concentric contraction or muscle shortening is negative, smaller than the maximal velocity of the contraction. So once again, those cross bridges won't just form. So that's why we equate velocity to 0. So now one thing here, each one of the scientists is using normalized axis. What is that? If you divide this relationship here, inequality, by Vmax, what you will get is V divided by Vmax is smaller than -1. So that is the notation we'll be using in the remaining part of the video too. So then what he's doing here is he's taking an interval from -1 to 0. So from -1 to 0 here. So that is where you observe muscle shortening, and fits a specific curve to this data right here. So the shortening will be modeled with this specific curve. Now, obviously, we're crossing the 0 and we're analyzing muscle lengthening, or the force generated during muscle lengthening. So for that, we have another equation. Now, don't get confused with these coefficients here. These coefficients are responsible for the curvature of this curve right here. So they may be different again for different species or for different muscles that you model, but oftentimes in the field, they're just set to 0.25 and 0.06. Now let's talk about Silva's equation. Silva described force-velocity relationship slightly differently, but used the same strategy. So for the velocity smaller than maximal concentric contraction velocity or the maximal velocity of muscle shortening, we'll be again setting force to 0, because that's what we observe physiologically, right? The cross bridges are just not on time to form. Now, for the region from -1, so that maximum negative velocity of contraction, to 0.2 to somewhere here, we're already in the region of muscle stretch, we'll be using this relationship of arc tangents. Why? Well, it fit data pretty well. So then in the third region, when we're crossing 0.2 and going up the axis of the velocities, we'll be using another arc tangent with some other constants. Now, what are the relationship of these curves between each other? So you can see that Thelin's curve is rising slowly and then saturates, something that we expect physiologically to happen. And then Silva's curve is rising up pretty fast. So now be careful and think through these curves when you're using them to model something. For example, if the velocity is changing rapidly in your simulation at small values, small increments in velocity will lead to big increments of force. If that destabilizes your model, don't use it. Use an alternative curve, either Thelin's or one of those we discussed before. Just to recap, today we talked about force-velocity relationship, which is just another property of skeletal muscle mechanics. We described the physiology behind this phenomenon and analyzed a plethora of formulas describing this curve. Hopefully you enjoyed the video, and I'll see you in the next one. Thank you for watching.